Gerai, tai labas rytas, labai malonu čia pas jūs būti. Ačiū labai Audriui ir Gediminui už pakvietimą atvykti į konferenciją iš Kalifornijos. Man visuomet labai smagu į Lietuvą atkeliauti ir su jumis pabendrauti ir pamatyti, ką jūs čia dirbat. Jūs labai gerai dirbat, man labai įdomu klausyti ir tai ačiū. Tai aš labai atsiprašau, aš šiandien angliškai kalbėsiu. Man prieš galbūt 25 metus, kai atvyko Kalifornija, Stepas Ašmontas man padovanojo fizikos terminų žodyną. Nu, aš visus neatmintinai išmokau, atsiprašau, Stepai. Tai man kai kada sunku, kai pradedu lietuviškai bandyti fiziką aiškinti, man trūksta tų terminų. Aš šią savaitę šiek tiek jų išmokau, tai labai ačiū visiems, kur mane mokino, bet man reikės angliškai kalbėti, tai atsiprašau. Bet jūs galite klausimus lietuviškai, jeigu norite. Tai gerai, tai kaip Audrius minėjo, aš dirbu astrofizikoje, bet aš taip pat dirbu su, gali sakyti, kietų kūnų fizika, solid state physics. Mes užsiemam su detektoriais, ypatingai superlaidėjai. Tai aš truputį apie tą papasakosiu. Okay, so now I switch to English, and of course you heard about this. Audrius mentioned it. This is a moment of great celebration for us at Caltech with the announcement a few days ago of the Nobel Prize for the detection of gravitational waves with LIGO. And you can see the my two colleagues, Barry Barish and Kip Thorne, the recipients of that award. And we'll be hearing more about that, I think, in a presentation later this morning. So I won't say too much about that other than we were very pleased and very happy. I'm sure we'll get a chance to celebrate. And my connection to Caltech goes way back. My father received his PhD in theoretical particle physics in 1963 from Caltech, and I attended the graduation ceremony. You can see me. That's me. I was 3 years old at the time. And Caltech has changed a little bit. Some of the buildings that you see in this picture no longer exist. There was an earthquake in Los Angeles in 1971, and the main administration building, Throop Hall, had to be torn down. So around that time, there was a physicist. His name was Bob Bacher. He was in charge. He was the division chair for physics, mathematics, and astronomy, and he was really responsible for shaping the physics department at Caltech after World War II. Up until then, it was really Robert Millikan. You probably know the oil drop experiment, measuring the electric charge. He was the one that was, you could say, almost president of Caltech. He was building the physics program at Caltech, and it was Bob Bacher after the war who took over. Bob had served in the Manhattan Project. You can see, of course, in these pictures, you know what he was doing. He was in charge of the physics division at Los Alamos and what was called the gadget division, and the gadget, of course, is that thing you see in the picture. He was part of the assembly team for the pit. That's the heart of the weapon with the special nuclear materials. So his hands were actually on that device right before that picture that you see there. And then he came to Caltech and he started building the department. And one of the first things he did was to hire Richard Feynman to Caltech. Of course, he knew Feynman from working with Feynman at Los Alamos during the war, and then later he ended up hiring Murray Gell-Mann, both of whom went on to receive Nobel Prizes in the 1960s, 65 for Feynman and 69 for Murray Gell-Mann. So this was the guy in charge of physics when my dad was studying there. And then, of course, Feynman, 10 years later, gave the famous Feynman lectures that you heard about. Here you can see a photograph of what those lectures look like, and you see Feynman lecturing. And you can see the 3-volume set. How many of you have read anything out of those books? Okay, so you know those books. These books are lovingly maintained by my good friend Michael Gottlieb, who edits them and keeps them going forward. And if you look in the audience, you'll spot a few people wearing ties, like me today. So those are the professors They're not the majority, but there's a few of them, especially in the back. You can spot them because these lectures were, word was getting around that these were interesting, and so the professors started to show up as well. Well, today, I teach that class in that lecture hall that Feynman taught. This is what it looks like now. It's been remodeled a little bit. I can only escape to Lithuania for about a week. I have to return to my students. They're waiting for this class. So I would be in front of this lecture hall teaching to those freshman students. And if you take a close look, see if I can get this to work. Right here, you see this railing. If you look close, you can see that it's in the center, it's in the form of a Feynman diagram. So it's a reminder of where we are. And then if you look over here, you can see there's actually a painting of Feynman, and he's holding one of these diagrams. And when I look up, sometimes I'm afraid that he's about ready to throw it because I said something wrong. So you have to watch your step in there. So exactly 40 years ago, I was an undergraduate student listening to this course, Physics 1, when I started as an undergraduate at Caltech. And I had the chance, as Audrius explained, to work on the Voyager project, which you see pictured here, a spacecraft that flew past the planets. I did a little bit of work on calibrating an electron spectrometer, and it was that spectrometer that the data from that instrument was one of the pieces of information that was used to decide that the spacecraft has actually left the solar system and has entered interstellar space. The spectrum of the electrons changes because the magnetic field is no longer dominated by the sun. So you can see the date down here, 1981. That's when I was a senior at Caltech. And that project, Voyager, was built at the Jet Propulsion Laboratory, which is part of Caltech. It was a laboratory that was started in the 1930s, initially with experiments on rockets, and then by the late 50s, the work changed to developing spacecraft to study planets. When NASA was formed, JPL was brought into NASA as well, so it's a kind of a joint Caltech-NASA arrangement. And so here you see the laboratory. In talking to some people here at the conference, I realized that maybe not everybody knows what JPL, the Jet Propulsion Lab, is, so I thought I would show this picture. I spent 6 years working here as the chief technologist, so my job was to be looking forward into the future and thinking about what technologies the laboratory would need for the missions and to make sure that we were making the right investments and working on those technologies. So you can see my office when I was doing that. You can also see on the right a building labeled the Micro Devices Lab. So some of the work I'll talk about today, the devices are made in that laboratory. I served as director of that lab for 4 years before the chief technologist position. And so you probably know one of the things that JPL did was this Curiosity rover landing on Mars about 5 years ago in 2012. And you can see my colleagues, Adam Stelzner and Miguel San Martin, getting pretty excited about the fact that they didn't make any mistakes. Okay, now Audrius mentioned that when I was a student in 1981, I took this course, General Relativity, from Richard Feynman. It was a graduate course, Physics 236. And eventually, we got around to learning about gravitational waves, and Feynman he handed out to the class this letter that he had written 20 years earlier. It was a letter addressed to Vicky Weisskopf, a famous physicist at MIT, and you can see what Feynman is saying. Some time ago, you asked me about radiation of gravitational waves, so Feynman had been working on that topic at the time in the early 60s. The next sentence is, this is a very late answer. I'm sure we've all tried to say that in various ways in our own emails and letters when we haven't got to things on time. But then if you read down, you can see I'm studying the problem of quantization of Einstein's general relativity. So he's trying to bring quantum mechanics and general relativity together. And then the next sentence is something about details of handling divergent integrals. Well, as you all know, this problem has never been solved. Still, it's an outstanding problem of physics. Feynman made headway on this in the early 60s, but even Feynman couldn't crack it at the time. So he's giving us this letter to Weisskopf. It's a long letter. It's about 15 or 16 pages long. And on the last page here, you can see what's written. He's starting to talk about the possibility of experimental measurements of gravitational waves. And he says about that, "I've not seen any plans for any such experiments except by crackpots." Okay. So he handed out this letter to the people in this class because we were learning about gravitational waves. Now, as you saw in Physics 1, professors would show up in his Physics 1 lectures in the 60s. Well, this was no different. There were students in the class, but they were professors, there were postdocs, there were all kinds of people. One of the persons who would show up is this guy, Stephen Hawking. Here you can see him pictured next to Sheldon Cooper from Big Bang Theory. Of course, you know that Big Bang is set at Caltech, and Sheldon is supposed to be working at Caltech. So Stephen Hawking would roll up in his wheelchair in the back of these lectures when we were listening to Feynman. And so were these guys. These guys would sit right in front of me, and the chair's right in front. On the right is Ron Drever. He passed away earlier this year. Had he not passed away, I think it's extremely likely he would have been one of the Nobel Prize recipients, because he was one of the key people in starting the whole LIGO effort at Caltech. The other guy on the left, Stan Whitcomb, actually, when he was an undergraduate at Caltech, he finished in 1973, he designed that electron spectrometer that I later worked on. He designed that electron spectrometer that flew on the Voyager mission, and he designed that as an undergraduate. His undergraduate project flew into interstellar space. It's pretty remarkable. But Stan is the chief scientist of LIGO. He recently retired from that position. He essentially worked on LIGO his entire career, and he's really one of the key people that made it work. And he was at the time an assistant professor at Caltech, and these two guys had just gotten hired to start the gravitational wave program at Caltech. They would sit in front of me, and Feynman was telling them that they were crackpots. So that's what I remember about that. Well, then there's one other sentence I'll highlight, and Feynman is talking about how experimentally you might be able to see whether gravitational waves are really quantized, and probably the best chance of that would be to detect the so-called B-mode polarization of the cosmic microwave background, which would be an imprint of gravitational waves produced during the era of inflation in the very early universe at about 10 to the minus 30 seconds or so after the Big Bang. If you could detect those B-modes, you could start to make some statements about quantum mechanics and gravitational waves. So I'll touch only a little bit on that in my talk. Okay, so after Caltech, I went to Berkeley and I got involved in astrophysics over there. Here you can see a photograph of me with my little research group. And I was getting involved in astronomy. You could say high-frequency radio astronomy or long-wavelength infrared astronomy. We were doing spectroscopy of the interstellar medium, star-forming regions, and like every good Lithuanian physicist, I worked with a laser. And you can see our instrument up there, and we were measuring spectra of atomic carbon and ionized carbon in star-forming regions, flying on this airplane that you see pictured here. It was a flying observatory operated by NASA called the NASA Kuiper Airborne Observatory. Well, this was a lot of fun. It was a good experience for me, but we had to work very hard to get the measurements that you see over here, pictured here, these spectra. And the sensitivity of our instrument wasn't very good. And that was because our detectors that we were using were not very good. They were semiconductor detectors, gallium arsenide Schottky diodes. And the lesson that I learned from my graduate school experience was that we really needed better detectors. And so that's what I decided to do as a postdoc. And I moved to Illinois, to Champaign, Illinois. And being a Californian, I was not familiar with scenes like this white stuff I'd hardly ever seen in my life, so I had to get used to that. This was my advisor, Fred Lowe. He ended up being the director of the National Radio Astronomy Observatory in the US, passed away also recently. And I started working on superconducting detectors using tunnel junctions, superconducting tunnel junctions. But there was time to do other things. So here you see a photograph of what we did in our spare time. I joined the local Lithuanian folk dance group and participated in the folk dance festival in Canada in 1988 when I was a postdoc. The woman you see standing to my right is my wife Ilya, also a Lithuanian American. And some of the other people that you see here pictured were the students or postdocs at the university as well. And Illinois was a good place to come to learn about superconductivity because that's where John Bardeen was. And there was a lot of activity. Of course, it wasn't just John Bardeen, it's everybody around him that had come. There was a very strong effort in solid-state physics. There were people working both on the theoretical and experimental side in superconductivity. It was a great place to come to learn about superconductivity. And I very much enjoyed being there and learning from the people there. One of the persons who was there was a man by the name of John Tucker, who in the 1970s had developed the quantum mechanical theory of the detectors that we were using with these tunnel junctions. And here you can see essentially what's involved. You can see the energy diagram. You have a superconductor on one side of the tunnel junction, a superconductor on the other side. The superconductor has an energy gap just like in a semiconductor, and it's because the electrons are paired in the superconductor. And the idea is that a photon can come and provide the energy that's missing for an electron to tunnel across the tunnel barrier, and you end up getting 1 electron of current for every photon, which is absorbed in the tunnel junction. So it's essentially a photodiode. You'd get 1 electron per photon. And the details of the quantum mechanical operation was worked out by this man, John Tucker, and here you see in his own handwriting some of the simpler equations in his theory. It's a lot more complicated if you go into detail, but you get a feeling for it here. John also recently passed away in 2014. I had the really wonderful opportunity to get to know him. He came to Illinois in a very interesting way. He was working in Los Angeles at the Aerospace Corporation when he developed this quantum mechanical theory of photon detection using tunnel devices. And most of the people that he was surrounded by at the Aerospace Corporation didn't understand what he was doing. They couldn't understand his mathematics, couldn't understand his lectures. But John Bardeen was serving on the visiting committee and came to Aerospace and listened to his lecture and thought it was pretty good. And a few years later, John Tucker received a phone call, and he answers the phone, and the voice at the other end of the line says, "Hello, this is John Bardeen." And Tucker thinks, "Bardeen, are you kidding me? Is some friend playing a prank?" And so he responds and he says, "Yes, and I'm the King of England." Well, it really was John Tucker. I'm sorry, it was really Bardeen inviting him to come apply for a position at Illinois. So that's how he got there. Tucker also was an undergraduate at Caltech in the 1960s. He missed those Feynman lectures, the 61 to 63 Feynman lectures, by a year or two. So he wasn't actually sitting listening to those lectures, but it was just a few years later. However, he had his own interactions with Feynman. As it turned out, there was a period of time for maybe a week or two when it turned out that they were dating the same woman. And Tucker became famous around Caltech for that. Okay, so I better move along. Starting in the late 70s and moving on into the 80s, there was work at Caltech by the people you see pictured here, Bob Layton and Tom Phillips, developing millimeter and submillimeter astronomy using these tunnel junction devices. And so I came in 1990 and started working on that as well. And you can see some of the photographs of the work that we did. The devices, as I mentioned, were produced using the facilities at the Jet Propulsion Lab, the micro devices laboratory there. And so we developed these tunnel junction detectors and solved various problems, built an instrument, flew it on this same NASA Kuiper Airborne Observatory that I mentioned. Here you see our liquid helium cryostat. The instrument is mounted on the back of the telescope. We flew around, and it was a lot more fun because the sensitivity now was way better. It was a factor of 25 or so improved over what I had done as a graduate student at Berkeley. And ultimately, that led to our involvement in an instrument that flew on the Herschel Space Telescope, the Herschel Space Observatory. Here you see the launch. You see the photograph of the spacecraft, and here is a big tank of liquid helium that was needed to cool all the instruments. And this is the device that we supplied, roughly 1 terahertz, 1.2 terahertz superconducting tunnel junction mixer for that. The same technology, I'll just briefly mention this little bit of science that was done with this instrument, the detection of water vapor from Ceres. Ceres was visited in 2015 by a JPL spacecraft called Dawn. And as Dawn was approaching Ceres, there were these very strange bright spots that were visible. And now the idea is that these bright spots are salt deposits that were left behind as the water underneath the surface evaporates. Here you can see the spectral lines of water being detected by this instrument on Herschel. Of course, the same technology, the superconducting tunnel junction detector technology, what makes ALMA work. ALMA is the world's largest investment in ground-based astronomy. It's a sub-millimeter interferometer located in Chile on a high plain, roughly 5,000 meter altitude, roughly, in rough numbers, a $1.5 billion investment. And it fundamentally relies on the superconducting tunnel junction detector technology. So by the late 90s, we were wrapping up our work on developing this tunnel junction detector technology. It was getting ready to be flown on Herschel, and I was starting to think about other things to do. And the big discovery around that time was the discovery of so-called sub-millimeter galaxies. These are galaxies which are extremely bright at sub-millimeter far infrared wavelengths, but are often essentially invisible to telescopes like the Hubble Space Telescope. And here you see an example of that. The image in the background is from the Hubble, and then the contours show you the location of the sub-millimeter object, and you essentially don't see any optical emission from that object. It's a galaxy that's undergoing a giant burst of star formation, but the star formation is entirely hidden by the dust clouds from which the stars are being formed. And so the idea was to think about how to do this better. They had a detector array, which was 37 elements in size. It was hand-built, very painfully hand-built, very difficult to build. And the question was, can we find a way to build detectors much more easily and to build a lot more of them so that we can take images of the sky much more rapidly? And so that's what we started to work on, and that was work that I've been involved with for the past 15 years or so, the so-called kinetic inductance detectors. And here you see such a detector array now. Instead of 37 elements, it's some 500 elements, and it's very easy to construct. And so the basic concept is shown here. I'm not going to go into all the ins and outs of the physics, but just give you a brief idea of how this works. You can see a patterned superconducting film. In this case, it's titanium nitride. You can use other superconductors as well. A portion of this pattern, this meander, represents an inductance. Down at the bottom, there's an interdigitated capacitor, and the two together form a resonant circuit at microwave or radio frequencies. And the idea is that if you shine light, if you absorb light on the inductor, as you see here, the frequency of that resonance shifts. The absorption of light in the superconductor causes the inductance of the superconductor to change, and you can use that as a detector. And one of the nice things is that you can frequency multiplex these devices. As you see here, there's a readout line that makes its way past all the pixels, and over here you can see all the different resonances, the 500 or so resonances of all the different pixels in the array. And so with a single readout line, you can access all 500 pixels simply by choosing the excitation frequency. It's a quite simple way to do it. Very easy to produce these devices, and you can make them also very sensitive. And so a little bit more about the physics. The idea is that in a superconductor, you have mostly electron pairs carrying current. The pairs are superconducting. They don't scatter. They don't give you a resistance, but they give you an inductance. And so that's this part of the circuit. Occasionally, some of these pairs may be broken into single electrons. The electrons do scatter, therefore they give you resistance. That gives you this resistance in the circuit. And so essentially you can think of a superconductor as an inductor and a resistance in parallel, and the inductance and the resistance depends on what fraction of the electrons are either in pair form or in single electron form. If you absorb photons, as you see here, the photons can break the pairs, so you can change the balance between pairs and single electrons. That means you're changing both the inductance and the resistance, and that's what causes the resonance frequency to shift. To make this work, the photons have to have energy above the energy gap, but that's fairly easy to do. Those frequencies are fairly low in the millimeter range. The tricky part is actually being able to measure the very small change of inductance, because it is very small. There's a formula, a simple formula here. This is the fractional change in reactance or the fractional change in inductance. There's some factors in here that have to do with the electrodynamics. They're of order unity. The important factor is here. It has to do with what fraction of the electron pairs are actually being broken. If you're an astronomer, you want to detect very faint signals, and so the rate of photons landing on this device will be very small. You'll be breaking a very small fraction of the Cooper pairs, and so this factor that you see, the second one, is very small. And so the question is, how do you measure a very small change in inductance? Well, it's fairly simple if you use a resonant circuit. It's a fairly easy measurement to make. And so we built a camera. You can see here, I'm going to go through these fairly quickly. This is the detector array. The cables going in and out, bringing the readout signals in, bringing them out. You have to have electronics to generate the readout signals and to measure them. These days, it's quite easy to do. For instance, using field programmable gate arrays, you can program them to do the signal processing. You can take the instrument to the telescope. In this case, it's our 10-meter telescope on Mauna Kea, a sub-millimeter telescope. You can see one of our team members hiding here. The people down in front are tourists who are coming to see the sunset, the beautiful sunset on Mauna Kea. Here's our instrument. You can see over here mounted on the telescope. And here's an image of the moon. It actually works. This was one of the first things that we did when the instrument was put on the telescope, just to check. It's an easy, bright object. And then you can start doing other things. Here you see some images of star-forming regions. If you looked in the visible, you really wouldn't see very much because, again, all of the action is happening deeply buried inside these dust clouds. And so I'm reaching the end. So I'm going to spend just a few minutes telling you where this technology is headed. By now, there's some 24 groups around the world working with these detectors in some a dozen countries or more. You can see various projects. There are instruments that have been built and deployed on large telescopes like this 30-meter millimeter wave telescope in Spain, telescopes in Chile. There are balloon-borne instruments being built using this technology. There are efforts to develop detectors to measure the microwave background. Polarization that I mentioned might be one way of getting at the quantization of the gravitational waves. There's an effort at the bottom that you see. ESRON is the Space Research Organization of the Netherlands. This is a large European Union-funded effort to develop these detectors for use on a space telescope, on a far-infrared space telescope. So there's now lots of activity in this field. Ourselves, one of the things that we're doing is trying to introduce these detectors into an integrated chip spectrometer. Very briefly, you can see here's a photograph of an instrument that we built for our observatory in Hawaii. It's a grating spectrometer in which the grating is sitting between two metal plates. It's a waveguide grating. The entire thing has to be cooled to 100 millikelvin. It's a fairly large piece of metal, and it has to be cooled to 100 millikelvin. And you see all these wires over here are to read out all the detectors. So it's a rather complicated thing. What we're trying to do is to replace it with this little chip. It's about 1 centimeter square. It does the same thing, except it does it all using superconducting circuitry and integrating these superconducting detectors, and our goal is to study the universe at fairly high redshifts, basically getting at the very first galaxies that we're forming. So this is one example of a project. A former student who worked on these detectors early on is now a professor at UC Santa Barbara. He's interested in using the detectors in the visible wavelength range. So when a photon lands, a single photon lands, you get a pulse. The size of the pulse is a function of the wavelength. Here you see a longer wavelength photon, a shorter wavelength photon. You get excellent time resolution. You never make a mistake. Either a photon lands or it doesn't. There's zero read noise in these detectors. And he has an instrument here you can see mounted on the back of the famous Palomar. It used to be called 200-inch telescope. It's now the 5-meter telescope. This was the largest telescope in the world for many years before the Keck telescope on Hawaii, the 10-meter telescopes, took over. And the goal here is to use these detectors to image exoplanets, to use the excellent energy resolution and time resolution to make direct images of exoplanets. So that's an interesting direction. I'm personally interested in seeing these detectors used on a space telescope. In 2013, I was part of a NASA study to look 30 years into the future. What could NASA be doing in astrophysics? One of the ideas that was put forward was a larger and also cold far-infrared telescope. We're now in the process of studying that mission, as you see over here. We're going to need sensitive detectors and lots of them. So that's an interesting possible future thing. I'll only very briefly mention this. This is kind of a sideline. The properties of the superconductors that we were using turned out to be very favorable for building very low noise microwave amplifiers. In fact, these amplifiers reach the quantum limit of sensitivity. And so we've been working on that. And that's led to ideas about how to use them for dark matter detection. This is a former student, Saptarshi Chowdhury. You can see the title of his paper, Radio for Hidden Photon Dark Matter Detection, that may take advantage of these very low noise amplifiers. There's also different ideas about how to use these kinetic inductance detectors for an entirely different way of searching for dark matter, being put forward very recently by these famous theoretical physicists from Stanford and elsewhere. And I don't have much time to get into it. Can I take another minute to describe this others? So there's also a connection with quantum computing. You probably know that the story of quantum computing starts with this famous paper that Feynman wrote in the early 1980s. In fact, when I was taking that course, that's when he wrote that paper. And then the real breakthrough came a little later when Peter Shor found an algorithm for how to use a quantum computer to factorize large numbers. Well, Peter Shor was my classmate at Caltech. This is the photograph from the yearbook, our graduating yearbook, and then later he went on to develop this algorithm. And these days, there's a lot of interest in superconducting quantum computing. Much of that interest is the result of this guy, Rob Scholkopf. He is my former student. And what he did was to take these very high quality factor superconducting resonators that we developed for detection, and what he did is he applied them to the problem of making a superconducting qubit by coupling the resonator, as you see over here, to a device known as a Cooper pair box. It's essentially a superconducting two-level atom which is coupled to a superconducting cavity. And here you can see an article from the New York Times talking about how IBM wants you to be using these quantum computers in the near future. And you can see the same kind of meandered resonators that we were using some 17, 18 years ago. And so I'll stop here. It's the work of very many people, and obviously it's not just me, and there are a number of articles. If you're interested, you can go look up. Thank you. And sorry for going over.
Labai dėkui, Jonai. Iš tikrųjų, gal nesupyksta, kad mes uždrėsime ir tikrai verta truputėlį nuėsime kavos laiko. Tai dabar tikrai klauskite, gal Darius irgi nesupyks, kad mes turėsime laiko klausimams.
I'll try to share. So your early observations were from a plane-based observers. So clearly there are problems with atmospheric absorptions, but yet all the latest work is on a
Yes. So the problem is water vapor, absorption by water vapor. So the best option is space. The next best option is a balloon. The third best is an airplane. The last is being on the ground. Of course, the costs of building things goes exactly in the opposite order. So you do what you can on the ground. You can find windows, atmospheric windows in wavelength or frequency, which lie between the water lines where you can do reasonable work. And that's why this big ALMA interferometer is in Chile, is because it's particularly dry there. It's a good site for doing this kind of work.
Yeah, so I also wondered, so of course these applications for the detectors that you mentioned, they are all very highly strung, and for astronomy, NASA budgets and so on. But I wondered if there would be possible to bring this technology more towards the mass market by using maybe high temperature superconductors and detecting somewhat higher light levels, and maybe terahertz as well. So could you comment on that?
Yes, so at JPL, we're particularly interested in that. One of the applications would be either on a planetary mission or an Earth science mission. There, the problem, again, is budget, surprisingly enough. It may be different kinds of budgets depending on the application. In the case of a planetary spacecraft power, the power budget on the spacecraft is a big issue, especially if you go far from the sun. The energy you can get from your solar panels becomes a problem. In that case, you can't afford necessarily to run a cooler which brings you to 4 Kelvin or below. You'd like to operate at a higher temperature, maybe just use radiative cooling, avoid any power at all. And so a high temperature superconducting detector like this would be extremely interesting. We've done some work on that. There are various technical issues involved, how you make them sensitive, but I think they're good prospects.
So maybe to add on that, so how many technologies from the JPL have broken into the mainstream in the past?
How many technologies from JPL?
Have there been any?
Yes, so let me tell you a few. This is a fun question. Thank you, Audrey. So you all have I'll give you an example two examples that relate to your cell phone, okay? One of them has to do with how your cell phone communicates. Now you know that it sends radio waves, but it communicates digitally. Well, in 1964, 1965, JPL was sending a spacecraft to Mars, and it had a television camera that was going to take pictures of the surface of Mars, and those pictures needed to be returned to Earth, and that had to be done digitally because you wanted not to mess up the pictures.
Is that the mission where they got the face?
That was the 1965 flyby called Mariner 4, which another Lithuanian played a very important role. Arvydas Kliorė, but I can talk about that later. But so the problem was how to send the pictures back. That had to be done digitally. They did that at about 8 bits per second. It was pretty crude, but this problem of digital communication was one that JPL focused on quite a lot in those early days in the late 50s, early 1960s. One of the engineers working at JPL at that time was a man by the name of Andrew Viterbi, who went on to found Qualcomm, and that's where much of the technology that's used, the so-called CDMA, code division multiple access technology, was developed, and it was because he'd gotten this training at JPL in communication. Another good example that relates to your cell phone has to do with the camera that's inside your cell phone. You all probably know that there's a little CMOS imager, a silicon imager that records the image. That technology was invented at JPL, and again, his name is Eric Fossum. He's in the U.S. National, the Inventors Hall of Fame. He's received a number of awards for this. But the problem was, how do you shrink the size of the cameras that you put on spacecraft? And that was a problem in the late 1980s, early 1990s when he was working. And so he invented this way of making the CMOS imagers you could make on a standard CMOS production line. And now they're used everywhere.